the observatory. She's a PhD student of Ziyu Zhang and Xiaoting Fu. Maybe you remember Xiaoting visiting us past years, and she's visiting us also this week.
She was here.
She's here for a work. Yes.
Many years ago, when we were in.
Yeah, I think 4 or 5 years ago, something like that.
More than that. I remember her maybe in the Morasut, but I don't want to bother.
No. We were.
But I remember very well. So.
But anyway, so she's talking about her PhD project about determination of isotopologues in high-redshift objects and the connection with the determination of the stellar initial mass function.
Okay, thank you, Donatella. Actually, you can call me Z Guo because my name pronounced as the same letter Z.
Just Z.
Yes, because the voice Z sounds really like Z. So just for simplifying the word. I'm a PhD student in Nanjing University, and here I'm very honored to show you about my recent work. Maybe I should say here. Which is first detection of CO isotopologues in high-redshift main sequence galaxies, indication of top-heavy IMF. So because have asked, I will explain again that CO isotopologues means 13 CO and C18O, which is the molecule of C and carbon and oxygen isotopes. So first start with some, okay, this not work.
Okay.
Got it. Okay. See? Okay, so start with some backgrounds just to make sure everything you can understand. First, here is the stellar initial mass function. So I think I don't need to explain more. And stellar initial mass function is a number distribution of the stellar mass in a single stellar population. And here I present the most popular IMF in the world, which is the crucial IMF, right? IMF is a very important assumption in many kind of fields because we always need it to connect it from stellar physics to the galaxies. If we assume an IMF, we can from the stellar evolution integrated to the single stellar population. And if we add the star formation history, we can finally get the evolution of the galaxies. So in recent research, we have found that there are kind of variations in the IMF. Like if there's more massive stars, we will call it the top-heavy IMF, which is also what we have found in the high-redshift main sequence. And here's some different methods to constrain the IMF because we have to say that in some research it's variation. So the most direct method is to count the stars. We just count the stars with different stellar mass. But this method is only valid in the Milky Way and also the LMC. And there are also some indirect way like SED feeding and CO isotopologues, which is also the method I'm using. So in some theoretical work, they have already found that the IMF is changing with the star formation rate. In the left panel is the results from IGIMF theory. The figure is from Yan et al. 2017, and you can see that the x-axis is the star formation rate of the galaxy, and the y-axis is the absolute value of the IMF slope. So if this value is higher, which means the slope is steeper, so there's a top line IMF. And if this value is lower, which is also what we see when the galaxy have a higher star formation rate, it means that the IMF is more top heavy and have more massive stars. This is also being proved by the observations. The right panel is a figure from Zhang et al. 2018. The x-axis is the infrared luminosity of the galaxy, which we know that represents the stuff emission rate. And the y-axis is the certain CO to CA ratio, which represents the IMF. And I will explain the reason later, but now I can say that the higher ratio of certain CO to CA represents more bottom-heavy IMF, and lower ratio represents a top-heavy IMF. You can see that all these galaxies have these trends that if they have higher stuff emission rate, it tends to have lower isotope ratio or the isotope ratio, which means they have more top-heavy IMF. And also we know that the stuff emission rate is evolving in the cosmos with the redshift. The left panel is a Madelon plot, and you can see the x-axis is redshift, y-axis is stuff emission rate density. It means that the stuff emission in the cosmos is actually evolving, and it's arrived a peak at around redshift 2, which we also call the cosmic noon. And in the right panel is the main sequence for different redshifts. You can see that different colors are different redshifts. And if we see with the galaxies with the same stellar mass in higher redshift, the stuff emission rate can be 10 times higher than in local or in local main sequence galaxies. So for now, we know that the stuff emission rate will change with redshift. The IMF is changed with the stuff emission rate. Then what is the IMF in the high redshift main sequence galaxy? We know that main sequence is the majority of the cosmos, right? So what is the IMF? Are they still the same with the Milky-Way IMF or the local main sequence IMF? And that's our main science question. To solve it, we select some samples. There are 4 galaxies. They are all the high redshift main sequence galaxies. Here is a comparison of them with their main sequence. You can see they're all located in the main sequence. And, and also they are all strongly lensed. Their magnification factor is over 10, which means that their signal is magnified over 10 times, which can guarantee that we can detect them. And also they all have strong CO emission detection. In the right panel is our continuum map of these 4 galaxies. You can see the contours are the continuum contour, and the background is the infrared image. Only 2 galaxies have continuum detection, and in these 2 galaxies, we have only 1 robust detection. Here, the galaxy is SDSS-J0901. Here is the spectrum of this galaxy, and you can see here is the ratio. Its ratio is around 2.4. The 13 CO to C18 ratio is around 2.4. And if we compare this ratio to local main sequence, you can see here is the local main sequence isotopic ratio, and around here is our observation. So this ratio is lower than in local main sequence and Milky Way. And also we do some more analysis of our results. You can see these 3 maps. They are the 12 CO, 13 CO, and C18 map, the background. And the foreground, they are all the continuum contour. For these 2 images, only these 2 parts seems more stronger, right? These 2 parts are the strongest image. But for C18, it's like these 2 images are the strongest. So why is it different? Is there some kind of like spatial distribution of the galaxy? So we compared our results with the lensing model from Sharon 2019. You can see in the right panel, this is what the galaxies looks like on the image plane, which means we directly observed. And this is what the galaxy really looks like, which means its real shape. And also you can see that this crossing it represents the center of the galaxy. And if we corresponding this center to the image plane, to what we see, and you can see that this center is corresponds to these three crossings. So what if we consider these two images with the crossings as the central region of the galaxy, and this image without the crossings as the outer region, and extract the spectrum separately, what can we find? So here is the spectrum, and also the ratio we have got, and you can see that it's kind of like some discrepancies of the isotopic ratio in different parts of the galaxy. Like the central region is around 1.9, the outer region is around 2.9, but the arrow is very large, so we cannot say that it's IMF distribution or something like that. But we can make sure that maybe the galaxy is not fully homogeneous, but we can know that the IMF in the whole galaxy is more top-heavy than the Milky Way and local main sequence. And maybe just compare the results, the isotopic ratio is not enough, right? We still need more theoretical proof. So we are using a method called galactic chemical evolution model. Here, I will briefly introduce it. It's like that most of the elements, the chemical abundance is created from the stars, from the stellar nucleosynthesis. So if we just mimic this process, like from the molecular clouds, a bunch of stars form. And in these stars, the stellar nucleosynthesis creates new elements. And through the stellar winds, through the explosions, these chemical elements just released to the ISM and polluted these molecular clouds. And these clouds can create or form the new generation of stars. Like it's a cycle, right? After cycles and cycles, the chemical abundance of the galaxies is evolving. So we use model to try to mimic this process, and we can use the final integrated results in the ISM to compare with our assumption to constrain the IMF. So here is our model results. You can see the different colors represents the different IMF we are using. And here is the star formation history we are using. They are flat, they keep the same star formation rate. The specific star formation rate value is kind of different because we are trying to make sure that all the galaxies will form the same alive star mass at this point, which is also the Hubble time of this galaxy. They are the same, so the star formation rate is slightly different. And in the third panel, it's the oxygen abundance evolution. You can see that only red lines and black lines across these data, and they are top-heavy IMF and Milky Way IMF. The fourth panel is the isotopic ratio evolution, and you can see that only red line across the observation data. So we say that the IMF in the high-redshift main sequence is more top-heavy, but there's still some question, right? Because the star formation history is very simple, maybe they can make some degeneracy. So also we do some tests with the different star formation histories. You can see here, with the different star formation history, we still make sure that they have the same alive stellar mass at the Hubble time of this galaxy. And we can concentrate on the different type of star formation histories. You can see that there's an increase, decrease, flat, and also an extreme starburst star formation history. And if you see here, You can see this black line actually across the data point. It's the galaxy with Milky-Way IMF and an extreme starburst. But this starburst is around 1,000 solar mass per year, which is contrary with our data of the submission rate, like the infrared luminosity. So we see that this galaxy cannot have a Milky-Way IMF because only if it has a very extreme starburst, which we do not observe. But still, actually, there are many degeneracies in the models because GCE model is not as simple as only IMF and submission history. There are still more. So let's just come back to the stellar yields. Here I show the IMF weighted stellar yields, which means that the stellar population is normalized to 1 solar mass, and we just check the production from different massings of the stars. And you can see different color represents different metallicity, and whatever the metallicity is, most of the carbon-13 is produced from the low and intermediate mass stars. And
what yields are those?
Okay, we are now using the Caracas 2010 and Nomoto 2013, the supernova yield.
Do you think it would be worth to try things from other authors? Or,
Sorry, you mean use what?
do you think, I mean, are the Caracas yields the only ones in the literature, or are there others that might be worth trying?
You mean if other yields worth trying?
Yeah.
Yeah, that's also the next point. So yeah, it's okay, it's okay. Just actually, most of the oxygen agents from massive stars. So as you said, maybe we do not believe in this stellar yields table, right? Maybe because there are a lot of stellar yields tables and they use different stellar models. Maybe this can make some discrepancy. And so we come back to the stellar nucleosynthesis. Okay, you can see the most of the carbon-13 is from single cycle 1 in this place. And most of the oxygen 18 is from single cycle 3 here. So from cycle 1, cycle 2 to cycle 3, they need higher temperature. And we all know that the stars with higher mass, their internal temperature will be higher, which means that if the star have lower temperature, then the majority of single cycle will be cycle 1. And if the temperature is higher to the massive stars inside of them, the majority will be still cycle 3. This will not change with the different stellar physics. Sorry, the stellar physics change maybe. With the different stellar models or the different stellar yields, the nucleosynthesis will not change. So we still can believe that the carbon-13 is most likely from the low mass and intermediate mass stars. So that's why we say that the IMF in high-redshift main sequence is more top heavy than the Milky Way and local main sequence. So that's all, and here's my summary. Thank you very much for listening and welcome for questions.
So questions for the speaker? Okay.
Yeah, if you go back to maybe the second one, when you define the slope of the, sorry.
This
Yeah,
one?
yeah, the alpha 3 is the slope of what? You assume a single power law IMF or two slopes?
Yeah, it's the broken power law of Krupa. The alpha 3 is here.
Ah, the alpha 3 is the high stellar mass slope. Okay.
Yes.
And what's the difference between the line, this C13O versus C12O line in wavelength, in shape, in intensity? I mean, how can you distinguish between two lines from the same molecule, but two different isotopology. Whatever.
You mean 13 CO and say 18 or 12 CO and 13 CO? I'm not very sure if I catch
No.
this.
Is-
Let's see. This one?
Yeah. Okay. The one is, the first one is 13C
Yeah.
and O is 18, no, which is the standard O, 16, I don't, is 16, yes.
Yes,
I'm
it's
sorry.
16.
Okay, and the other one is C12 O 18.
Yes.
And the very standard one, C12 and O 16,
It's not here.
is not here, but
Yes.
it's a different wavelength. I mean, it's easily,
Okay,
you can easily distinguish between
Yes,
the
yes.
various sizes.
Because its frequency is quite different and not here. And if you want the line width, I heard here are the line widths for 12 CO, 13 CO, and 16.
Okay, this is the line, but the line width are very different.
Yes, the line width is 30.
The one with the C12 is much more intense. It's 8.8. Is okay.
Please.
Yes, do you have plans to increase the sample to give other lens galaxies? Is any hope there are new catalogs of lenses around? Do you have plans to look for more cases like this? Because then you have just one attention.
Actually, we are planning. Yeah, it's in the plan. And because it's really hard to observe, for these galaxies, I think we like spend 2 hours in Alma for average. Yeah. So it's quite hard because Alma time is very bad.
May I ask one question? Because I don't know if before this slide or at a certain point you show that actually you have a sample.
Sample, yes.
So exactly this one. So I was expecting that. So this is part of the sample that you selected,
Yes.
and you selected to be on the main sequence at that redshift. Okay, and so I guess my question is related to what was asked before. So you were planning to have detection in all these 4 objects, and you didn't get a detection, or it's just that this is the sample, but then you did a pilot project and then select just one galaxy and then you will follow up others. So my question is, what the others are not observed or are not detected?
Not detected. We
Not
observed
detected.
all the galaxies. These 4 galaxies were all observed.
Okay.
Yes.
And
I
from
can see if I have the figure for backup. Oh, sorry, I don't have. But yes, we observe all of them, but only one have detection.
And so the follow-up question is the fact that you did not detect anything tells you something about, like, you can gather information from the non-detection on the IMFs and on all the discussion that like you did for the detected one, or like, I don't know, putting an upper limit, the fact that you don't detect this molecule means something in terms of production of elements, or just because maybe they are just faint, this is my curiosity.
It's kind of interesting because we don't want to waste this time and also the observation data. Actually, we can get the upper limit of 13C, 13CO and C18 because they are on the same line. You can see that. But because for these 3 galaxies, these 3 undetected galaxies, both 13CO and C18 are non-detection. So if they are all upper limits, that means nothing, right? Because it cannot constrain the ratio at all. So we can kind of constrain the ratio of 12CO to 13CO, but if we want to get more information, it's very difficult because 12CO have more problems. You know that this line is optically thick, and if you want the abundance, it's not as easy as the optically thin lines. So yes, we kind of have some interesting upper limits, but actually nothing can done for now.
Okay. Any other question?
Really last one, and it's on the same, let's say, subject. The only galaxy that you detect has some particular characteristics. I mean, it's just because it is brighter, or has some other, in comparison to the other three, has some, let's say, sublimation rate higher, has some.
Yeah, actually, this galaxy is this one.
Ah, okay.
You can see it have higher stellar mass, it have higher sublimation rate,
Okay.
it's brighter,
Yes, yes.
so
Okay.
it's just from this one.
Any other question? Let me check if there is any question from, no, okay, no. I'm just checking here. Okay, so if there are no any other questions, let's thank the speaker again.